Hi guys, we're back to talk more about sedimentary rocks, and this time we're going to kind of talk about sedimentary classification of different rocks. So let me share my screen as always. Okay, so first of all, we talked about what a sediment is, and so we're going to think about how different kinds of sedimentary rocks form and how we would classify them. But just briefly, I want to mention that these different sediments often in different landscapes become soil, which is a group of sediments that's mixed with organic matter and air and water, and that special mixture allows life to be able to kind of live in the soil, and then the soil is able to support plant roots and support plants and ecosystems. And so soil is one potential kind of outcome of a sediment's life. And so a lot of those sediments that are in soil, that form soil, originally formed from rocks. They weathered, they were transported across the landscape, they were deposited, and then they became soil. So we know soil supports different landscapes. Here's a picture of the state soil of California. It's called the San Joaquin Soil Series. Here's a picture of it in profile, and here's a picture of it on the surface. And basically we get soil because of the same kinds of chemical and physical weathering processes that we've talked about. But then if we want to form soil instead of a sedimentary rock, we need the presence of organisms to be introducing different kinds of organic acids, to be introducing nutrients, to be leaving behind organic waste. And those organisms are going to continue to mix the sediments. There needs to be the presence of oxygen, and the continued presence of organisms living and growing within these loose sediments that start to be mixed with more and more organic matter over time keeps them loose and unconsolidated. So that's different than what we see when sediments end their life as a sedimentary rock. And of course, some sediments that are in soils might eventually become sedimentary rocks. But in this case, there's the same sort of chemical and physical weathering. There's the same potential transport. There's the same potential deposition. However, what happens in the case of sedimentary rocks is there is a lithification process. And the lithification process usually involves several steps. The first is burial. So usually these sediments get buried away from the surface, away from the presence of oxygen and organisms. And because of that, they don't have a buildup of organic material. They don't have contact with oxygen that allows for lots of organisms to live at those depths. And then they start to have what's called the precipitation of different kinds of minerals in between the sediments. And the precipitation of those new minerals starts to cement and hold those sediments together, or lithify them, which just means turning them into a rock. And so usually it's this kind of disconnect from the surface, this burial, this disconnect from oxygen, this disconnect from organisms that allows the sediments to stay in place for long enough for then these precipitating minerals that are usually moving through groundwater to start to cement and hold those sediments together to form sedimentary rocks. So when we think about what kind of sedimentary rock we're looking at, we usually have different kinds of ways that we can observe and try to classify them. So one way is by clast size. So clast is just a word for the piece that is cemented together. Clast composition. So is this made of a pretty pure mineral? Is this made up of different kinds of feldspar-based sands? Is this made up of organic material? Is this made up of shell material? So that's going to be composition. And then there is concepts of angularity, which is how sharp or angular are the different fragments, the clasts that end up being cemented together. Are they angular, or are they rounded or smoothed? And then fourth is sorted. So are all the clasts within this particular rock a pretty similar size? Or is there a big variety of big, medium, and small pieces all glued together? And then the character of the cement, whatever, is it calcite? Is it silica? What's the agent that's holding the pieces together is another thing that could differ between different kinds of sedimentary rocks. So usually if we can identify a little bit about these 5 characteristics, we can probably identify the rocks and understand also then a little bit about their history. So when we think about size, there's actually a very kind of precise way that we can differentiate between different sizes. You can see over here, these are different sizes in terms of millimeters that we assign to these different names. But generally, we know that clay, which is often contained in things like mud, is just a very, very fine, meaning a very, very small piece of inorganic matter, less than 0.002 millimeters in diameter to be considered a clay. Then there's silt, which is another kind of thing that might be in a mud. That's like a very fine piece of sediment. Also probably too fine to really see with your naked eye, from a 0.002 to 0.05 millimeters. There's 10 millimeters in a centimeter. So like even smaller than half a millimeter is silt. So also kind of microscopic, but bigger than clay. And then we get into sand, and sand you can usually see with your naked eye, right? If you have sand in your hand, you can actually pick out the individual grains, and we can have finer sand, we can have coarser sand, larger sand, then we can have kind of granules, which are like between sand, and then like pebbles, and then cobbles and boulders. So there's actually a very precise way that we can differentiate between the sizes of what's in a sandstone as opposed to granules and pebbles that would form a conglomerate, as opposed to like silt and clay that might form like a shale or a siltstone. So there's ways that we can classify the different sediment sizes. As I mentioned before, angularity is something that refers to how either sharp or rounded are the edges of the particular clasts. And angularity usually tells us a little bit about the pathway, the history of the clast. So generally, the longer that that clast has traveled since it was originally weathered and broken off some sort of parent rock, the more rounded it's going to be. So you can imagine the journey across like 100-mile river from the mountains to the beach is something that's going to have a lot of bouncing around, and all that bouncing through the river is going to kind of smooth off sharp edges. And so usually when we see like river rock, it's generally rounded, or if we get all the way to like the beach down here at the kind of delta or like the entrance of a river where it meets the ocean, we'll usually have quite a bit of fairly rounded pieces of material, which would be quite different compared to the kind of sharp, jagged, talus type slopes that we would see where rocks first break off from some sort of like mountaintop or other geologic feature. So for instance, here is like what we would call like a talus slope or a scree field. These are rocks that are just kind of breaking off again from a steep mountain usually, and then they're kind of piling up. They haven't really tumbled very far. They haven't been smoothed. And when these rocks form a group, get cemented together, we call this breccia, as opposed to conglomerate, which is a rock of more smooth, rounded, like river pebbles and cobbles that get cemented together. Okay, so another example is sorting, or another characteristic is sorting. Sorting tells us, are all the pieces the same size, or are they different sizes? And this also tells us something about the history of the clasts and sediments that kind of join to form the particular rock. So the better sorted the materials are, the more likely it is that they have traveled a farther distance, which is similar to rounding. And then if the sediments are less well sorted, then it's likely that they came from a position that was more close by to where they ended up being lithified. And the idea is that as materials move along the landscape, their size is going to influence how they end up moving, particularly in water, which is of course the agent that does a lot of moving of sediments across the landscape. So like in a flood, for instance, the flood can carry all kinds of big boulders, as well as rocks, as well as pebbles and sand and silt and mud and all different kinds of sizes. But then as a flood kind of recedes, what we'll see is that the biggest sized rocks kind of fall out of the river flow first. They stop moving. The river doesn't have enough energy to continue to push them. And then next, like the cobbles will fall out, and then the sand, the next biggest size, will fall out after that. And then it might take a really long time for the really fine pieces, like the silts and the clays, to fall out. And so when we look along a river, we can often see that there's different areas of the river that are like a gravel bar or a sandy beach or a muddy bank. And the river over time has been sorting and separating out these different materials based on the speed of the water moving past that particular point. And so basically, the better sorted these things are, as we just mentioned, the more likely it is that they've been already moved across a landscape a particular distance. So this sand on the right is all very fine, all similar material. So this didn't break off a mountaintop, all perfectly ground to the same size sand, but it did some journeying across the landscape, and then the movement, particularly through water, was able to sort materials and gather all this sand together. Whereas this particular conglomerate, which is right by the beach, which might be confusing because you might think, oh, these rocks have traveled a long way to get to the beach. Well, probably in this case, there's a smaller watershed, and these materials have come down some sort of mountain and traveled through some sort of river because they're rounded. So they've done some transport, but then they have been lithified or cemented together in this environment where they have been like shaken up, and they haven't been moved enough after that original formation or that shakeup to kind of re-separate out. So this is a poorly sorted on the right versus well sorted on the left. And then finally, we mentioned cementing. What are the agents that are cementing? So usually calcite and then silica, which is basically quartz, are the two main things that cement the different clasts or sediments together. Calcite tends to dissolve more easily, and silica is a little bit harder, more resistant to that chemical weathering process that would break down the calcite. And so when we're thinking about this, I just want to point out that you've probably seen the precipitation of calcite before, which would be the same kind of process that happens in the presence of groundwater or surface environments, where these minerals are precipitating and potentially gluing sediments to other nearby sediments. And you've probably seen this before, like on faucets or on shower heads, when water that came from the ground, from some sort of well environment that probably had lots of dissolved calcium in it, comes out onto the surface, and the different temperature and pressure environment on the surface allows the calcium to come out of solution and starts to precipitate on your water fixtures. So when we see this, we call it hard water, but this is the same kind of thing that's happening in different geologic environments to form sedimentary rocks over long periods of time. And then you can see here some chemical weathering taking place. Okay, so we can talk about sedimentary rocks based on these characters that we just mentioned, but then there's one other way that we kind of classify them that I want to mention, which tells us a little bit about like what the materials that went in that make up the rock, like what are the class made of, essentially, which is one of the fifth thing that was on my original list for this presentation. So the first type of rock we call clastic sedimentary rocks. And these clastic sedimentary rocks are having clasts that are made up of just like very standard mineral rocky material. And so this would be like your classic sandstone, your classic siltstone or conglomerate. And then depending on size, we might classify it as a conglomerate or a breccia, a sandstone or siltstone or shale. And you've likely heard of these different terms before, and I'll have these examples set up for you guys to look at for lab this week. But clastic sedimentary rocks aren't the only kind. There's also chemical sedimentary rocks, which are sedimentary rocks where the clasts, the pieces that make up the sedimentary rock, weren't really transported across the landscape as like large sized sediments that we could see easily, but they were transported across the sediment or across the landscape as dissolved little like ions and compounds in water, usually. So in groundwater or surface water. And then as the temperature or humidity or pressure changes, they will start to precipitate out of solution, or the water that they're dissolved in will start to evaporate and they'll be left behind as evaporates. And so many of the minerals that we learned about often form big expanses of like big salt beds, or big like gypsum or travertine outcrops. And the travertine is a type of calcite, basically. Dolomite, calcite. Anyway, but these minerals are considered sedimentary rocks, chemical sedimentary rocks, because they have pretty pure chemical compositions, but they exist on the landscape because of the transportation of these different compounds from some other rock that they were originally part of, that they dissolved from through chemical weathering. They move to a new place, and then they kind of retransform or reform a new kind of rock. And so halite, calcite, gypsum, travertine, etc., could be considered in this category. So one local example that you may have seen before is called soda rock by some people. And this is a rock that exists along Indian Creek in between the Y and like Crescent Mills. And it has some importance to Maidu culture, but it's kind of a notable feature along the side of the landscape. And this is a place where some sort of likely like limestone reserve has been dissolved into groundwater, and then groundwater is kind of coming out basically in like a spring type of environment here, and then it's precipitating out on the surface to form this travertine compound, which is like calcite with a little bit of magnesium in it. And it forms these interesting like stalactites and stalagmites that you might see in a cave environment. Those are usually limestone environments too. And so anyway, this is just an example of what a chemical sedimentary rock might look like. Okay, we also have rocks that we call biochemical sedimentary rocks. So these are rocks that form from compounds that don't contain their own DNA, but were made by living organisms, which is basically like shells and exoskeletons. And limestone is the main rock that falls into this category. It has the same composition as the calcite mineral that we've learned about. But in particular, we call something limestone if the calcite that's contained in the limestone came most recently from the shell of an organism. And so we can have different kinds of very fossiliferous limestone, where it contains a lot of evidence of different kinds of, you know, the organisms that broke down to form the limestone. Coquina is one example of like limestone that has lots of very recognizable shell fragments in it. Micrite is from like a mud, a limestone that's ground really finely down into mud, then is cemented. And then chalk, which we use for many other purposes, is a form of limestone, and it is formed from little tiny plankton, very fine plankton, calcium carbonate based shells that get cemented together. So if you go to many tropical places and you look at the sand on the beach, what you'll notice is it has a very different composition than the sand at many like mid-latitude beaches like you would see in California. And what you would see when you look at the sand up close is that it's primarily made up of lots of these shells. And that shell material is what is eventually getting cemented together to form these different limestone features. This is a picture in Vietnam, and this is showing these limestone cliffs, which are really kind of a classic feature of a lot of the areas in Southeast Asia. Another kind of biochemical rock is called chert. Chert is the same thing, but instead of being made from calcium carbonate based shells, it's made from silica, like glassy based shells. So more chemically similar to like quartz. And we often call these rocks cryptocrystalline, meaning like invisible crystals, because the crystals in these rocks are so small you can't see them, unlike many other sedimentary rocks where you can like see the different kinds of clasts. And that's because they're made up of the exoskeletons of microscopic organisms like different diatoms and radiolarians, which are different kinds of like plankton that live in the ocean that have these glassy shells. And there's all these like beautiful photographs from high-powered microscopes looking at these different plankton under the microscope, but you can see they have all these really beautiful glassy shells, and these shells settle out usually in the deep ocean as opposed to kind of shallow ocean environments, which is where mostly limestone is forming. But in these deep ocean environments, all this fine silica-based material settles out into this like silica-rich mud, basically, and then it gets cemented together to form chert. And then over time, as different geologic and tectonic processes are occurring, then some of this material that forms in the deep ocean is uplifted. And so we can see it in many places along the California coast. This is in like Golden Gate National Recreation Area, just north of San Francisco. You can see all these like beautiful chert layers. And many tribes in California have historically used chert as a really sharp implement, kind of similar to like obsidian for like knives and arrowheads and stuff. So it has that kind of like glassy quality to it, similar to obsidian. Okay, finally, we have another group of rocks, which are kind of rock imposters, and we call them organic, so within the category of biochemical rocks, but they're specifically organic biochemical rocks. And when we originally defined what it meant to be a rock and to be a mineral, a building block of a rock, we said you can't be organic to be a rock. So these things are not truly rocks, but they exist in these sedimentary rock environments. And so we study them alongside sedimentary rocks. And these are made up of ancient plant and animal material, so contains that organic compounds. And these are things like fossil fuels, which means like coal and natural gas and oil. And basically these organisms have been buried, just like other sediments, for long periods of time and cut off from oxygen and cut off from organic matter that might serve to break this material down. And over long periods of time, being buried away from the surface, these materials get compressed, they get heated, they get pressurized, and they chemically transform a bit. And we have different names for kind of different stages along this kind of metamorphic process, this change process. And so first of all, we can have peat, which is a layer of material that is really very similar and resembling like old plant matter. We can really like see the plants in it. And then lignite has been heated a little bit more and has been pressurized a little bit more, but it still has some of those kind of potentially recognizable like plant fragments in it. And then by the time we get to coal, there has been adequate heating and pressure that we really wouldn't recognize any of the organic material anymore. And all of these things can be burnt to release the organic energy, the energy that was originally in these plants. And that's one of the ways that we create energy. Other fossil fuels like oil and natural gas are typically formed from plankton, ancient plankton that have been buried and pressurized and heated over periods of time to form those forms of fossil fuel. So we'll talk about all this a little bit more later, but while we're talking about different sedimentary rocks, I wanted to acknowledge that these organic sedimentary rocks are often studied alongside the other sedimentary rocks. Okay, it's a good stopping point.